Hello.
Hey.
Oh, beautiful. Looks like a Christmas tree. Sorry I can't ride with you the rest of the way up, but this is where my dad works. Well, have a good time. Oh, I forgot to give you a hug.
Elevators are cool to use and a good substitute for escalators. The physics of them are easily explainable and fun.
We're not gonna play a game where you have to decide if I'm moving at constant velocity or stationary. Right now, my weight is 500 newtons at rest. I'm in an elevator without windows. My weight is still 500 newtons. Can you tell if I'm moving at constant velocity or if I'm at rest?
Trick question. There's no way to tell which one is happening. The forces balance each other, so the normal force, which is the weight, is still 500 newtons and her acceleration is 0. However, acceleration is 0 both at rest and constant velocity, so without any reference points, there's no way to tell which one is occurring.
My weight at rest is 650 newtons. I'm now going to go into an elevator accelerating upwards at 1.5 meters per second squared. What will my weight be? Will it be greater than, less than, or equal to my stationary weight?
Using Newton's second law and a free body diagram, we can solve for n when Tommy is traveling in an elevator accelerating upward at 1.5 meters per second squared. I set up as the positive direction and n turns out to be approximately 750 newtons. This will mean he will feel heavier and his weight will appear to be more than his actual weight.
You got it, Gina. My weight is greater than my stationary weight. I now weigh 750 newtons.
Tommy is now accelerating downward at 6.5 meters per second squared. To solve for his weight on the scale, we start by drawing a free body diagram and draw the tension from the cord and the force of Tommy's weight acting downward. Next, we use Newton's second law to find the sum of the forces and solve for Tommy's normal force. His new weight should be 219 newtons.
You got it, Nikki. My weight is now less than it is when I'm stationary. I now weigh 219 newtons. Nikki is now going to cut the elevator cord. Once that happens, the apple and I will start to float. Nikki, you're going to cut the cord?
Rest in peace, Tommy.
Oh!
Tommy had a rough ride, but momentarily he got to feel weightless. Taking a look at Newton's second law and the free body diagram, accelerating at 9.8 meters per second squared, his normal force would equal 0. Tommy experienced normal forcelessness, at least until he hit the ground. This is essentially how astronauts feel when they are in space.
If you ever find yourself on a free-falling elevator, never jump up before the elevator falls. Instead, lay flat on the ground so the force of the impact is spread throughout your body evenly.
I'm now accelerating at 19.6 meters per second squared, and I'm on the ceiling! Help me! Help!
When the acceleration of the elevator is greater than 9.8 meters per second squared, I get pushed up towards the ceiling because my acceleration remains 9.8 meters per second squared until my fall to the bottom.